Download this code from codegive.com, link in the description below. Boyer-Moore string searching algorithm, a detailed tutorial. The Boyer-Moore algorithm is a highly efficient string searching algorithm known for its speed, particularly when searching for long patterns in relatively long texts. It's often considered the most efficient general-purpose string searching algorithm in practice. Unlike simpler algorithms like naive string searching or the knuth-morris-pratt (KMP) algorithm, Boyer-Moore gains its efficiency through two key techniques. One, looking from right to left * instead of comparing the pattern from left to right, Boyer-Moore starts comparing from the rightmost character of the pattern. This allows for larger skips, especially if a mismatch is found early. 2. Preprocessing heuristics, bad character heuristic and good suffix heuristic. Before the actual search, the pattern is preprocessed to create two lookup tables. These tables are used to determine how far to shift the pattern when a mismatch occurs. The algorithm chooses the larger of the two shifts suggested by these heuristics. Let's break down these concepts in detail. 1. The basic idea and right-to-left scanning ***. Imagine you're searching for the pattern example within the text. This is a simple example text. The naive approach would start comparing example with this I, then his is, then is a, and so on. Boyer-Moore, on the other hand, would first align the rightmost character of the pattern, E, with the corresponding character in the text, example. When aligning example with this is **, it would then compare the pattern characters from right to left. If a mismatch occurs, example, if the current character in the text doesn't match the expected character in the pattern, the algorithm uses the heuristics to determine how many positions to shift the pattern to the right. 2. The heuristics ***. The core of Boyer-Moore's efficiency lies in its two heuristics, the bad character heuristic and the good suffix heuristic. 2.1. Bad character heuristic, also called bad symbol heuristic. This heuristic tells us how far to shift the pattern to the right based on the mismatched character in the text. Scenario 1, the mismatched character in the text does exist in the pattern. Find the rightmost occurrence of that character in the pattern. Shift the pattern so that this occurrence aligns with the mismatched character in the text. Scenario 2, the mismatched character in the text does not exist in the pattern. Shift the pattern so that the character in the text just before where the comparison started is aligned after the rightmost character of pattern. The pattern can be shifted to entirely past the mismatched text character. Example **. Let's say our pattern is Anpanman and the text is "This is a nice Anpanman" text. We align the pattern at some position in the text. Let's assume we're comparing the pattern, right to left, with the text at the alignment shown above. We encounter a mismatch, the character in the text, C, doesn't match the character in the pattern, N. The bad character heuristic asks, does C exist in the pattern Anpanman? The answer is no. Therefore, we shift the pattern entirely past the C. In this case, we'd shift the pattern 8 positions to the right. Now, let's consider another example where the mismatched character does exist in the pattern. This time, the mismatched character in the text is B. The bad character heuristic asks, does B exist in the pattern Anpanman? The answer is no. Therefore, we shift the pattern entirely past the B. In this case, we'd shift the pattern 8 positions to the right. Now consider this scenario. This time, the mismatched character in the text is P. The bad character heuristic asks, does P exist in the pattern Anpanman? The answer is yes. The rightmost occurrence of P in the pattern is at index 2, remember indexing starts at 0. Asterisk therefore, we shift the pattern so that the P in the pattern aligns with the P in the text. This results in a shift of 5 positions to the right. Implementation details for bad character heuristic asterisk. To efficiently use this heuristic, we preprocess the pattern to create a bad character table, also called a bad symbol table. This table stores the index of the rightmost occurrence of each character within the pattern. If a character doesn't appear in the pattern, its entry in the table will be -1, or some other suitable not found indicator. 2.2. Good suffix heuristic asterisk asterisk. This heuristic is more complex but often provides even larger shifts. It considers the suffix of the pattern that has been successfully matched before the mismatch occurred. Asterisk scenario 1, the matched suffix occurs elsewhere in the pattern. Asterisk find the rightmost occurrence of the matched suffix in the pattern, but not overlapping the current occurrence. Asterisk shift the pattern so that this other occurrence aligns with the matched suffix in the text. Asterisk scenario 2, a prefix of the pattern matches a suffix of the matched text. Asterisk if there is no complete matching suffix, consider partial matching. Find the longest prefix of the pattern that matches a suffix of the matched text. Asterisk shift the pattern so that this prefix aligns with the suffix of the matched text. Asterisk scenario 3, no matching suffix or prefix exists. Asterisk shift the pattern to align the first character with the first character to the right of the rightmost character we initially tested. Example asterisk. Let's say our pattern is abob kebab and the text is, something abob kebabbed. Suppose we've matched the last 4 characters of the pattern, abab, but then we encounter a mismatch. Asterisk the good suffix heuristic asks, does the suffix abab occur elsewhere in the pattern abob kebab, excluding the occurrence at the end? Asterisk the answer is yes, it occurs at the beginning of the pattern. Asterisk therefore, we shift the pattern so that this earlier abab aligns with the matched abab in the text. Now, consider this example. Asterisk the good suffix heuristic asks, does the suffix ab occur elsewhere in the pattern abob kebab, excluding the occurrence at the end? Asterisk the answer is yes, it occurs in multiple places, right after the first ab, and then at the end of the pattern. Since we're excluding overlapping occurrences, we need to consider other options. Asterisk second, the heuristic asks, does a prefix of the pattern match the suffix of the matched text? In this case, it would consider, prefix of vs suffix b, no match. Prefix of vs suffix ab, match. Asterisk we've found a partial match. We shift the pattern until the prefix ab aligns with the suffix ab in the text. Implementation details for good suffix heuristic asterisk. Implementing the good suffix heuristic requires more preprocessing than the bad character heuristic. You typically need to compute 2 tables. Asterisk suffix underscore shifts, stores the shift values for scenario 1, suffix occurs elsewhere in the pattern. Asterisk prefix underscore shifts, stores the shift values for scenario 2, prefix matches suffix. The precise calculation of these tables can be a bit intricate and requires careful consideration of edge cases. 3. Putting it all together, the Boyer-Moore algorithm. Here's a step-by-step outline of the Boyer-Moore algorithm. 1. Preprocessing asterisk. Asterisk create the bad character table, using the bad underscore character underscore heuristic function below. Asterisk create the good suffix tables, suffix underscore shifts and prefix underscore shifts. We will skip the example implementation for this heuristic because it requires a lot of code and understanding. 2. Searching asterisk. Asterisk initialize the alignment of the pattern with the text, usually at the beginning of the text. Asterisk while the pattern is still within the bounds of the text. Asterisk compare the pattern characters from right to left with the corresponding text characters. Asterisk if a mismatch occurs. Asterisk calculate the shift amount using the bad character heuristic. Asterisk calculate the shift amount using the good suffix heuristic. Asterisk choose the larger of the two shift amounts. Asterisk shift the pattern by the chosen amount. Asterisk if all characters in the pattern match, a complete match is found. Asterisk record the starting position of the match. Asterisk shift the pattern by the amount suggested by the good suffix heuristic, to find potential overlapping matches. Python code example, with bad character heuristic only. This implementation focuses on demonstrating the bad character heuristic to keep the code manageable. A full implementation with the good suffix heuristic would be significantly longer. Explanation of the code asterisk. Asterisk bad underscore character underscore heuristic, pattern, this function creates the bad character table. It iterates through the pattern, storing the last index of each character in the bad underscore char underscore table dictionary. Asterisk boyer underscore more underscore search, text, pattern, this is the main search function. Asterisk it initializes variables like n, text length, m, pattern length, and matches, a list to store the starting indices of matches. Asterisk it calls bad underscore character underscore heuristic, to get the bad character table. Asterisk the while loop iterates through the text, trying to align the pattern. Asterisk the inner while loop compares characters from right to left. Asterisk if J0, it means a complete match is found. The starting index I is added to the matches list. The shift is then incremented by m, pattern length. This is the least optimal way to shift when there are overlapping patterns. Asterisk if a mismatch occurs, the bad underscore char underscore shift is calculated. Asterisk if the mismatched character exists in the bad character table, the shift is calculated based on the difference between the current pattern index j and the rightmost index of the mismatched character in the pattern. Max, bad underscore char underscore shift, 1, ensures that the shift is always at least 1. This prevents infinite loops in cases where the mismatched character is the rightmost character of the pattern, and therefore bad underscore char underscore shift would be 0. Asterisk if the mismatched character is not in the bad character table, the shift is j plus 1, which means shifting the pattern entirely past the mismatched character. Asterisk the pattern is shifted by bad underscore char underscore shift. Important considerations asterisk. Asterisk space complexity asterisk the bad character heuristic requires extra space to store the bad underscore char underscore table. The good suffix heuristic requires even more space for the suffix underscore shifts and prefix underscore shifts tables. In practice, the size of the alphabet, the set of possible characters, often limits the space used by the bad character heuristic. Asterisk worst case performance asterisk while Boyer-Moore is highly efficient on average, it has a worst case time complexity of O(m) \n, in some specific scenarios, example when the pattern and the text are highly repetitive. This is the same as the naive string searching algorithm. Variants like the Boyer-Moore-Horspel algorithm address some of these worst case scenarios. Asterisk alphabet size asterisk the performance of the Boyer-Moore algorithm is influenced by the size of the alphabet. Larger alphabets generally lead to better performance because the bad character heuristic is more likely to result in larger shifts. Asterisk implementation complexity asterisk implementing the good suffix heuristic correctly can be quite challenging. Many simpler implementations rely solely on the bad character heuristic, sacrificing some potential performance gains for reduced complexity. In summary asterisk the Boyer-Moore algorithm is a powerful and efficient string searching algorithm. Its performance relies on scanning the pattern from right to left and using the bad character and good suffix heuristics to determine how far to shift the pattern upon a mismatch. While the implementation can be more complex than simpler algorithms, the performance benefits often make it a worthwhile choice, particularly for searching long patterns in large texts. The code above provides a basic implementation using the bad character heuristic, which demonstrates the core principles of the algorithm.